In this class, I will explain an important function called Lagrange interpolation function. So this Lagrange interpolation function, it is defined in terms of natural coordinates. In the earlier classes, I had explained to you about the different types of coordinates that we are going to use in finite element analysis. One is the global coordinate system, local coordinate system, and natural coordinate system. In natural coordinate system, we use this zeta and eta for two-dimensional analysis, two-dimensional problem analysis. So this Lagrangian interpolation function is defined in terms of these natural coordinates, and it is used to derive shape functions of higher order elements. Higher order elements means suppose if you have a curved element, you can call it as a higher order element because the displacement polynomial used to define curved elements will be of the order 2 or more. Then this function gives more accurate results in the analysis, because when you go for higher order elements, naturally accuracy will be more because you are going for finer mesh refinement. So if you want to find distress at a point or displacement at a particular point, then if you use higher order elements, you will get more accurate results. Now the Lagrangian shape function can be defined like this. So np of zeta is equal to zeta minus zeta o into zeta minus zeta I dash up to zeta minus zeta p minus 1 into zeta minus zeta p plus 1 up to zeta minus zeta n divided by, in the denominator, that zeta term is replaced by zeta p term. So that means zeta is a general term. So that is the variable here in the Lagrangian interpolation function. For p is equal to I, so here p is any nodal point. I have considered a two-noded element, something like this. I and j, they are the nodes. That is, j is I plus 1. So here, suppose if I is 1, j becomes 2. If I is 2, j becomes 3, like that. So this function is defined in such a way that always this first node, at the first node, your zeta value will be minus 1, and at the second node, zeta value will be, second node means that is the n node, it will be, zeta value will be 1. So in such a way, this Lagrangian shape function has been defined. That's what he says here. For p is equal to I, that is at this node, your zeta value will be minus 1, whereas at p is equal to, p plus 1 is equal to j, that is j is I plus 1. In that case, the value of zeta is plus 1. So what I need to say here is, the first node and the last, first n node and the last n node, if you take it as I and j, always this function gives the value of zeta in the first node as minus 1, and in the last node it is plus 1. Now this we can apply to find the shape functions and to sketch the shape functions for different types of elements. Among that, I am going to take the first element as the bar element, which I have defined earlier that bar element is a one-dimensional element, and of course I will take 3 nodes for this bar element, 1, 2 and 3. The third node I have taken at the center of the element, and I have taken 1 degree of freedom at each node. Degree of freedom means it is the independent displacement that can happen at that node. So here I have taken degree of freedom maybe q1, q2, q3. So like that I have taken the degree of freedom. They are the nodal displacements. So since it is a one-dimensional element, and I will take 1 degree of freedom at each node, total degrees of that is freedom in the element will be 3, q1, q2, q3. Now using this Lagrangian interpolation function, let us find out the shape functions. So n1, n2, n3. For each node, we will be having one shape function. So at node 1, now I am going to use this. All of you observe, very important. If you understand this element, you can derive the shape function for any other type of element using this Lagrangian interpolation function or shape function, which is defined in terms of zeta. Of course, here it's a one-dimensional element. That's why I am going to use only zeta term. Suppose if you take two-dimensional element, then the zeta term also will come into picture. That I am going to explain later on. Now, how to use this? Now, first I will take this node 1. First node 1 I will take. At node 1 you can see here zeta 1 is the value of zeta 1 will be -1. So now if you apply this, how to apply I will tell you. So now I am finding this p is 1 now. So n1 of zeta is equal to, now here what happens here, there are 3 nodes here. So how to write this I will tell you. There are 3 nodes here, out of which the first node I am writing the shape function, n1 value I am writing. If you are writing n1 value, the other 2 you have to take. The other 2 nodes you have to consider. So like this, in the numerator it becomes zeta minus zeta 2 into zeta minus zeta 3. So zeta minus zeta 1 term won't come. Zeta minus zeta 1 term won't come here. Please observe here, when you are writing the shape function for the first node n1 value, so zeta 2 and zeta 3 terms will be there. Zeta will be common in the numerator. Divided by, in the denominator, you just replace that zeta term by zeta 1. That's it. So because we are writing the shape function for node 1, replace this zeta by zeta 1 here and here. So you are going to get the displacement, that is Lagrange shape function for the first node. So then later on we have to substitute the values. So numerator you see zeta 2 is 1 here. Here actually this is 0 because at the center I have taken the third node at the center. Zeta value at center will be 0. Here it is +1. Here it is -1. So what happens is you substitute those values. Zeta minus zeta 2 is 1 into zeta minus zeta 3 is 0. Divided by zeta 1 is -1. Zeta 2 is +1. So that means -1 it becomes into zeta 1 is -1. Zeta 3 is 0. So if you substitute this and simplify, you will get zeta into zeta minus 1 in the numerator divided by 2 in the denominator. So this is the shape function n1 for this element. Now on the similar lines, if you want at the node 2 shape function n2 zeta will be, now what you have to do is in the numerator, so zeta 2 you should not consider. Zeta 2 you should not consider. So zeta 1 and zeta 3 terms. So those 2 you have to consider. That means for whatever shape function you are writing the Lagrange interpolation in the numerator, so that node zeta value you should not consider. So other nodes you have to consider. So here you can see here in the numerator zeta 1 term will be there, zeta 3 term will be there, zeta 2 term will not be there. Divided by wherever zeta is there in the numerator, you replace it by zeta 2. So zeta 2 minus zeta 1 into zeta 2 minus zeta 3. Once again you substitute the values of zeta 1 as -1, zeta 2 as +1, zeta 3 as 0 in this, and if you simplify, you will get n2 as zeta into zeta +1 divided by 2. So here you can see this is zeta -1, this is zeta +1. That is the difference. Now coming to node 3, so that is the midpoint of that body element. So there, when you are writing for node 3, zeta 3 term will not come in the numerator. So zeta minus zeta 1 into zeta minus zeta 2 will be there. Zeta minus zeta 3 term will not come. Divided by wherever zeta is there in the numerator, in the denominator, that zeta it should be replaced by zeta 3. So zeta is replaced by zeta 3 here and here. So rest terms are same, and substitute once again these values and simplify. You will get 1 minus zeta square as the shape function for the third node. That means n3. So n3 value is 1 minus zeta square. So here one thing you should keep it in mind here is, so at node 1 the value of n1 will be 1. So at node 1, so the value of n1 will be 1. So that is the meaning. So at other points the value may be defined. Similarly, at node 2 the value of n2 will be 1, and at node 3 the value of n3 will be 1. So this is very important. We can judge, you can always draw, you can sketch the shape functions at the three different nodes. That also they can ask in the examination. Derive the shape functions for a three-noded bar element using Lagrange interpolation function, or in terms of natural coordinates, they may ask taking 1 degree of freedom at each node. So this is how they will ask the question, and sketch the variation of shape function. Now I will sketch now how to sketch the shape function. There are three shape functions here because there are three nodes, n1, n2, n3. So we have to sketch. Now already we have got the expressions for n1, n2, n3 in terms of zeta using the Lagrange shape function, interpolation function. Now let us see how we can sketch that. So for sketching the shape functions, we have to sketch them independently. First I will take the shape function n1. So draw the element like this, 1, 2, 3. Write down the values of zeta. Here it is 0, here it is 1, here it is -1. And write down the expression for n1. So n1 is zeta into zeta minus 1 by 2. That value you know here. So that expression we have already derived. Zeta into zeta minus 1 divided by 2. So this expression we have already derived. Now substitute the value of zeta at these points and get the value of n1. So what I have done here is, here I have taken the point, here I have taken the point, here I have taken the point, and I have taken midpoint of this. So if you take midpoint of 1 and 3, it is not a node. Please note that this is not a node. Just I have taken midpoint. So at the midpoint, the value of zeta will be half of, that is average of these two. So midpoint will be now minus 0.5 here, because this is 0, this is -1, this will be minus 0.5. Here the midpoint will be zeta as plus 0.5. Now what I have done here is, you can observe here, I have just gone substituting values of zeta in this expression, and I have got the corresponding values of n1. So if zeta is -1, n1 will be minus 1 into -1 divided by 2, which becomes 1. You can see, you can calculate that. If zeta is that the n1 value becomes 1 there, here, then at this point, zeta as minus 0.5, substitute here, you get minus 0.5 into minus 1.5 divided by 2, which becomes 0.375, which is positive. So please note that positive values I am plotting above the line, above the element. Next, zeta is equal to 0 at this point. So when you put zeta is equal to 0, n1 becomes 0. Therefore at this point it is 0. Then you have 0.5. Zeta is equal to 0.5. So you have the value of, if you substitute, you get the value of n1 as minus 0.125. This is the value. So negative means you have to plot below the line. Then at the last point, when zeta is equal to 1, here zeta minus 1 becomes 0. Therefore n1 becomes 0. So if you, these are the points now we got. This value is 1. This is 0.375, this is 0, this is minus 0.125, this is 0. Join this by a curve, because here the term is not a straight line, it is a curve. Throughout it is a curve, because zeta into zeta square term is there in the function, therefore it varies in a quadratic manner, so it becomes a curve. So just join this point by a curve. So this is the shape function. So this is the shape function for this shape function n1 variation from this end to this end of the element. On similar lines, you can get the variation of shape function n2. If you plot, n2 is given by zeta into zeta plus 1 by 2. So if you substitute the values of zeta once again 1, 2, 3, 4, 5 at these 5 points using this expression, because n2 is zeta into zeta plus 1 by 2, you will get the corresponding values as first value becomes 0, second value of n2 becomes minus 0.125 here, then third value of n2 becomes 0, fourth value 0.375, fifth value 1. So there is other way. So here once again it is, since it is parabolic variation, zeta into zeta plus 1 by 2 is a parabolic variation. So this also is a term. So like this you have to plot. And lastly, if you want to plot n3, So the expression for n3 what we got is 1 minus zeta square. 1 minus zeta square, of course, this is also a parabola. But what happens here? So at these 5 points, if you go and substitute the values of zeta and get the corresponding values of n3, here it is 0, here it is 0.75, here it becomes 1, here also 0.75, here it is. This of course it is symmetric. So symmetric about that vertical axis we are going to get. So this is how this is the n3 shape function. So n1 shape function will be like this variation, n2 shape function variation will be like this, n3 will be like this. All are terms because it contains zeta square term. So like this you may be asked to derive the shape function of any one-dimensional or two-dimensional element, and they will ask you to sketch the variation. Normally variation they will ask for one-dimensional element because for two-dimensional it will be very lengthy. So in the case of two-dimensional 2D element, so this eta also comes into picture. That I will take up in the next class. So please understand this carefully. So this is the procedure how to use Lagrangian interpolation of shape function to get the shape functions of higher order elements. So it's a very useful concept in finite element analysis. In terms of natural coordinates, we can always derive the shape functions of one-dimensional or two-dimensional or even three-dimensional element using Lagrangian interpolation function.